you can see, the title for my presentation today is slightly different from what was included in the proceedings. And this is one aspect of my research where I'm really talking about detecting spectral changes in burnt landscapes using hyperspectral remote sensing. This is how my presentation will run today. I'll start with a brief introduction on the importance of fires in the Australian landscape, and then discuss some of the research questions which I aim to address in this presentation, and then take you through some of the method section of my research, and then discuss some key results and findings, and wind up my talk with a few things I intend to do with the hyperspectral data. And starting off with the background. Now, fire is critical to the Australian landscape, and it's been associated with the Australian landscape for a very long time. And as you can see from the map there, that there's fire seasons all over the world in Australia. And because of this close association of fire in the Australian landscape, the Australian flora has come to rely on these fires for diversity, persistence, and even reproduction. However, on the other hand, we've got these uncontrolled, large-scale, catastrophic bushfires, which cause grave environmental loss as well as economic losses. And the most classic example that comes to my mind is the recent 2009 Black Saturday bushfires. So to mitigate this threat posed by these catastrophic bushfires, government agencies and land departments resort to prescribed burns. And the idea behind prescribed burns is to reduce the fuel load in the Australian forests, so that it reduces the severity of subsequent bushfires. And in doing so, they are able to protect both natural assets as well as built assets. So it's very important to get an estimate of these measures of severity, which is really the rationale for my research, that burn severity estimates are important parameters for carbon cycling and modeling. And one of the key things would be for the land managers, because they want to get information on how efficient their prescribed burn activities were. And then once they've carried out those burns, which areas of the forest are in urgent need of post-fire rehabilitation and remediation. So moving forward, as I mentioned earlier, what I'm presenting today is a small aspect of my research, but the overarching aim of my research is really to ascertain severity in Australian dry sclerophyll forests, using spectral and structural changes detected by the spectroradiometer and terrestrial LiDAR, respectively. However, for the purpose of today's presentation, I'm only going to focus on some results from the hyperspectral data sets. And the research questions are really around detecting which vegetation indices are most effective at measuring changes in burnt landscapes, and if there are any correlations that exist between vegetation indices and burn indices. Quick overview of my study area. It's located within School Road Reserve, St Andrews, and as you can see, it's not very far from where we are based out here in Melbourne. It's just approximately 36 kilometers from here. And as you can see from this photo, the forest type is typical of a Victorian dry sclerophyll forest with a very grassy understory and this absence of shrubs. As you can see, the forest is quite sparse, and the average height of the canopy in my study area was between 10 to 12 meters. And it was dominated by eucalypt species including longleaf box, red box, and red stringy bark. And this was, that's it, sorry. And within the study area, we had 4 different plots, and as you can see from the photos here, they were quite homogeneous in composition as well as being representative of the Victorian dry sclerophyll forest. And the idea behind choosing these 4 circular plots was that one plot was to act as control, and 3 other plots were to receive different fire treatments in an attempt to simulate different fire severities. And we at RMIT worked in close association with the land management agency involved in carrying out this fuel reduction burn in my study area. So when they were doing the burns, we were present in the field, and we basically liaised with the fire personnel and asked them to apply different fire treatments to the different plots in an attempt to simulate different fire intensities and severities. So, and within these plots, we had different targets flagged, and this is a diagram which shows how forest fuel is stratified vertically in Victorian forests. So it comprises the canopy fuel, the elevated fuel, which includes shrubs, And we've got the near surface fuel, which includes grass, and the surface fuel, which includes litter. So in relation to this fuel hazard, in each plot we had a target representative of the canopy, the near surface fuel in the form of grass, and a litter target. Because there were no shrubs present in our study area, we didn't really have any targets to flag for the elevated fuel. And in addition to all these targets, we had a bare earth target flagged as well, and 9 1 by 1 meter mixed land cover elements. And the hyperspectral instrument used was the ASD Field Spec 3 radiometer, which was used in the bare fiber optic mode with a field of view of 25 degrees, and was obviously operated at various heights to simulate different object views. And those are the product specifications. The spectral range was from 350 to 2500 nanometers, and spectral resolution was 3 nanometers at 700 and 10 nanometers at 1400 and 2100 nanometers respectively. Now the next couple of slides are around the results which I'm going to discuss, and I'd like to let you know that the results which I'm going to present are only from the canopy spectral measurements. And when I refer to canopy in my presentation today, I'm really talking about the canopy as well as the background understory, which is composed of grasses, litter, coarse woody debris before the burn, and a mixture of all these unburnt elements and ash and char. So whatever signals and results which I'm presenting now would have a background influence as well. So this is a quick overview of the spectral signatures obtained from the canopy targets from the 4 different plots. And as you can see, we've got the wavelength along the x-axis and reflectance along y-axis. There were 5 different data captures. The green line indicates the pre-burn, black in week 2, orange in week 6. We've got the 3-month data capture as well as the 1 year, which is highlighted in red. Now the first set of curves are from the canopy target and the control. As you can see, there's not much of a change in the shape of the spectral signature as such, although the intensity changes slightly, and that possibly could be attributed to seasonal variation as well as changes in solar illumination and angle, because this data capture took place within 1 year from the burn event. As we move on to the next plot that received a fire treatment, we again see that the shape of the signature doesn't change as much. It's just that the intensity changes, and I'd like to point something here that the canopy target that was chosen in plot 1 did not come into fire contact. It's just that the understory was completely burned, but the foliage wasn't scorched at all. So it's not really surprising that the shape of the spectral signature is quite similar to pre-burn levels. Now if we move on to the next 2 plots here, we see that there's an obvious change in spectral signature that can be observed as early as week 2 from the burn event. And there's loss in obvious spectral features that are indicative of green vegetation in the form of absence of the green reflectance peak and the collapse of the red edge, and you've got the water absorption features that have sort of disappeared. However, what is remarkable to note is if you look at the red spectral signal from the 4 graphs, it clearly indicates that 1 year from the burn event, the signature is back to pre-burn levels as far as the shape is concerned. It's slightly higher in intensity, and that is quite true for both the plots which received the fire treatment. So this to me indicates that week 2 is probably a very good time to try and monitor how severe the fire was, because you get to see that deviation from pre-burn levels. And 1 year from the burn event is really good because you can start to see vegetation recovery. And the next this particular slide is basically a photographic evidence of what I presented in my previous slide. So these photos up here are from the control plot, and as you can see, there's not much variation in the understory because it obviously did not receive any fire treatment. And the canopy looks pretty similar as well. However, if you pay attention to these 4 photos taken from a burn plot, you'll see that there's obvious changes in the understory. It's so grassy before the burn, and it's a mixture of ash and char after the burn. The entire canopy is scorched, and 3 months from the burn event, there's still no signs of regrowth, but the canopy has shed most of its leaves, and then 1 year from the burn event, remarkably, you see this flush of growth, and as the spectral signatures in the previous graph indicated, it's more or less back to pre-burn levels as far as the shape of the spectral signature was concerned. And this is attributed to the fact that these three species have epicomic buds in their bark. So when the fire exposes the bark, these epicomic buds are released and they produce clusters of shoots which develop into leaves, and they have all these fuzzy looking leaves all over the canopy. And one thing to note here is the shape of the canopy is a bit odd. It's not quite what it was pre-burn, and that is typical of these species, and over time they will recover their original shape. The next couple of slides I'm just going to talk about variation in some commonly used vegetation indices and trying to figure out which of these can actually detect the changes in burnt landscapes. So the first one, which is NDVI, and before I proceed with that, I'd just like to point out that the x-axis for all these graphs indicates the timeline at which the spectral data capture occurred, and the y-axis is really the magnitude of change observed by that particular index. So we've considered different sets of indices here. So we've got NDVI, which is a good measure of vegetation greenness. Excuse me. And as you can see, with the control plot, which is denoted in the blue diamonds, it's pretty constant and similar at around 0.6, and that sort of suggests to me that it's a pretty good baseline to compare our results to. And results from plot 1 are also quite consistent, and that makes obvious sense because it never came into fire contact. However, if you look at the other two plots, there's an obvious distinction between what was unburned and what was burnt. And again, as I indicated earlier, 1 year from the burn event, all the values are closer to pre-burn values. Tikari by Osawi is identified as a good indicator of chlorophyll, and however, for this purpose, there's no obvious trends that we can observe from there. And this graph here basically shows variation in the photochemical reflectance index, which is a good measure of carotenoids in foliage, and basically represents the photosynthetic efficiency of vegetation, and shows a good trend as well that control and plot 1, which did not come into fire contact and were unburned, remain pretty consistent throughout the field campaign, whereas with the plots that came into fire contact, there's an obvious change. It increases in week 2, goes on increasing to week 6, and then starting to recover and back to pre-burn levels in week 1. And with one of the other indices, carotenoid reflectance index, it's pretty much all over the place, so it's not really any trend that we can follow. And these are just some other vegetation indices which are related to measuring and ascertaining water stress. And quick answer to interpreting these graphs is they're all pretty good at detecting burnt targets from unburnt ones. If you look at vegetation, water index, moisture stress index, and the normalized difference vegetation water index, they all pretty much tell the same story. So it's pretty clear to say that NDVI, PRI, and some of these water stress indices are quite good at detecting targets that came into fire contact. In this graph here, I'll quickly try and draw a correlation between a burn index in the form of difference normalized burn ratio and DNDVI. And I'd just like to give you a brief overview of what I'm trying to explain here. So you've got these green dots here, which are basically points from the control, and you've got black ones like that, which are recorded 2 weeks from the burn event, orange week 6, the purple one 3 months from the burn event, and the red ones which are here 1 year from the burn event. And first thing that really strikes is you've got this clustering of green dots closer to the axis, and then you've got this clustering of red dots, and there's a range of DNBR beyond which it is an indicator of the fact that vegetation has recovered or it's an unburned point, and that is 0.1. So you can I've very quickly drawn just 2 clusters there, and this particular cluster really represents the fact that those are the points that really never that either never came into fire contact or have recovered sufficiently to be back to pre-burn levels, whereas these ones, which are quite widely spread, have come into fire contact, and the severity increases as early as 2 weeks from the burn event. And as you can see, that there's quite a strong correlation between vegetation index and the burn index, and it's represented as 0.88. So some of the key findings from my research today is spectral changes which are observed are quite obvious from week 2, and that's a good indicator if you're trying to ascertain severity. And as I've demonstrated, 1 year from the burn event is a pretty good time to monitor vegetation recovery. And some of the vegetation indices that I thought worked pretty well were NDVI, VRI, and some of the indices around water stress. There's strong statistical relationships between burn indices and vegetation indices, and had a very good R-square value of 0.88. So what this really means is, if there are satellite sensors out there which have high resolution spatial, which have a very high spatial resolution, they don't often carry the middle infrared band, which is used by the normalized burn ratio. So DNDVI can be used as a good surrogate index if you're trying to monitor fire effects on the landscape. And obviously, if you're trying to acquire satellite and airborne imagery for the purpose of severity and vegetation recovery, then the timescales that we've come up with are that week 2 is probably a good time if you're trying to study severity, and 1 year if you're trying to study vegetation recovery. So the next step forward is really to try and test all these correlations for the other land cover elements for which spectral data capture occurred in this research, which is the grass, the litter, bare earth, and then to draw correlations between these indices as well as field measures of severity. So we had field measures of canopy cover, canopy change, understory composition, pre-burn, post-burn litter depth, ash and char depth, and whatnot. And the other aspects which we're trying to investigate is spectral mixture analysis of mixed land cover elements for which spectral data capture occurred, and it's really trying to unmix the spectral signals into abundance of post-fire surface materials. And as I stated earlier, the overall goal is to ascertain severity. That's pretty much a brief summary of my presentation today, and I'll end here. Thank you. Any questions? Yeah.
So the spectral measurement is for understory, right?
Yes.
So how does the solar illumination affect your measurement? I mean, when you do your spectral measurement for the understory, right? So the overstory will take the effect of
Yes.
the spectral measurement.
Yes.
How have you considered that, or how to?
Yes, so as I indicated earlier, the forest is quite open. So the targets which were chosen for spectral reflectance measurements were selected so that there was clear sky view. So we ensured that whenever spectral data capture occurred, we had access to clear sky view. And when the spectral data capture occurred for the canopy, we really had the sensor sitting on top of the canopy to try and simulate the object view.
At least, how did you calculate burn index?
How did you calculate the burn index?
Yes. So the formula for the NBR is NIR minus MIR divided by NIR plus MIR. And we don't really have a hyperspectral index, hyperspectral version of the NBR. So for the purpose of this research, what we've really done is we've taken an average of those bands which are simulated by the Landsat TA. So we've taken an average